For this chapter, we'll talk about the Faraday's law. It's actually the final law for in the Maxwell equation, and in induction and energy transfer, induced electric field, inductor and inductance, self-inductance, power circuit, energy stored in the magnetic fields or in the inductor, energy density, mutual inductance. Okay. So first of all, it's about the Faraday's law and Lenz law. Okay, so let's look at the first experiment. It's something similar to the lab 2. Half of you have worked on the lab 2 weeks ago, and the other half of you will do it 2 weeks later, I think. So because there's so first of all, so there's a conducting loop. A conducting loop is connected to a sensitive ampere. So this is a conducting loop, and actually this is a loop, and this is a sensitive ammeter, which means it can sense very small current, because there's no battery or other source of EMF, no battery, and there's no current in the loop. However, if we move a magnetic bar magnetic to work the loop, the current suddenly appears in the circuit. The current disappears when the magnetic stops moving. It doesn't mean you remove it. At the moment you remove it, you will have current. But as long as you don't move, you just place it there and you don't move, then the current disappears. If we then move the magnetic away, a current again suddenly appears, but now in the opposite direction. So this is pretty interesting because we don't have battery. However, we can measure some current in this loop, because when we study the electrostatics, if we really need current, we need electric field so that to push the electron to move. However, for this loop, we only move a magnetic bar. Although the current is small, we need a sensitive ammeter to really measure this small current. So next, so if we experiment for a while, we would discover the following. Which means we can summarize some rules which are more concrete. A current appears only if there is relative motion, which means you need to move the magnetic or remove this loop. So that's between the magnetic and the loop, they have relative motion. The current disappears when the relative motion between them ceases. When they stop or they move together so that they don't have relative motion, then there's no current. So faster motion of the magnetic produces a greater current. If you can move faster, the current will get greater. If moving the magnetic north pole toward the loops causes clockwise current, then moving the north pole away causes counterclockwise current, which means the direction of the current is relative to the pole of the magnetic. If you move the north pole into it, you have clockwise, and moving away, you have counterclockwise. And if you use the south pole rather than the north pole, the direction of the current will be opposite to this case. So this is the first experiment, and the second experiment will be more similar to the lab you have done or you will done. So for this experiment, we use the apparatus with the two conducting loop rather than a magnetic bar close to each other but not touching. So these two loops are close to each other. If we close switch S to turn on the current in the right-hand loop, the meter suddenly and briefly register current, which means when we turn on this loop, which means there's an electromotive force, we have a battery, so that there will be a current going through this loop. And of course, the current of this loop is changing until actually it's a first order circuit. This is something like an inductor. This is a resistor. So the current will be something like if this is V, and this is R, this is L, the current will be something like V over R 1 minus exponential minus T L over R, something like this. Actually, you have worked on circuit analysis, and I will briefly introduce it later when we talk about the RL circuit. But it doesn't matter. The point here is that the current here is changing. When we close the loop, it will start from 0 to V over R. And the meter suddenly and briefly register current and induce current in the left-hand loop, which means when we open it, we have some current. And actually, these two loops is not touching each other, but we will register a current at this loop, something similar to the previous experiment. And if the switch remains closed, no further current is observed because the current doesn't change anymore. It will settle to this current. If we then open the switch and other sudden and brief introduce current appear in the left-hand loop, but in the opposite direction, because when we open it, then the current of this loop will exponentially decay to 0, which means there is some change for the current for this loop, and then the current of this loop also changing until sometimes later the current of this loop is 0, then this is also 0. We get an induced current only when the current in the right-hand loop is changing, either turning on or off, and not when it is constant, even if it is large. So it doesn't really matter how large it is, it only cares about how much it is changing. The induced EMF and induced current in this experiment are apparently caused when some changes. But what is something? Faraday know. Faraday's law of induction. Faraday realized that an EMF, electromotive force, and a current can be induced in a loop, as in our two experiments, by changing the amount of magnetic field passed through the loop. This loop, he further realized that amount of magnetic field can be visualized in terms of magnetic field line passing through the loop. So we also define the magnetic flux similar to the electric flux. We denote it as phi b through an area A. In magnetic field, E is defined as phi b is the surface integral of the magnetic field. something like that. But of course, according to the Gauss law of magnetic, if it is a closed surface, this term should be 0. However, we only concern the area of this loop, So where the integral is taken over the area, the SI unit for magnetic force is the Weber. Weber is T times meter squared. Hester times meter squared is what we call Weber. If B is perpendicular to the area and uniform over E, the flux is similar the multiplication between the magnetic field and the area. Actually, magnetic force is a scalar similar to the electric force. So for the Faraday's law of induction, the magnetic of the EMF induced in a conducting loop is equal to the rate at which the magnetic flux phi b through the loop change with time. So Faraday's law is something like the electromagnetic force is equal to the negative value of the first derivative of the magnetic flux, which means when the magnetic flux is increasing, it will induce a negative electromotive force. And if the coil has n turn, we just simply multiply n in front. So it is something similar to what you have seen on the lab manual. The electromotive force equals to the negative of the derivative of the magnetic flux. The induced EMF tends to opposite the flux change, and the minus signs indicate the opposition. This minus sign is referred to as Lenz law. So here we talk about Faraday's law and Lenz law. So this whole formula called the Faraday's law, but Lenz only tells that it should be a minus sign, then this is called Lenz law. So it will be fortunate if you're born 200 or 200 years ago. If you can find the negative sign, then this law is named after you. So you'll be fortunate. But now it will be very difficult to do scientific research. It's not possible if you find a negative sign. What does it mean? So this is the Faraday's law, and Lenz law tells you that it should be a minus sign. So let's see a simple problem. The long solenoid S has 220 turns per centimeter. Carrier current I. It is its diameter D is 3.2 centimeter, and at its center we place a 130 turn closely packed coil C of diameter D. The current in the solenoid is reduced to 0 at a steady rate in 25 milliseconds. What is the magnetic magnitude of the EMF that is induced in the coil C when the current is in the solenoid is changing? So this setting is something similar to the lab. Although you provide a AC signal rather than a DC or something like the current is reduced linearly. So let us make some calculation. So phi b, because as we know for solenoid, the magnetic field inside the solenoid is uniform. So we can simply use phi b equals BA
In the previous chapter, we know that the magnetic field is simply like this. It's simply like this. Mu I n. N is the number of turns per unit length. Unit length. So small letter means turn per unit length. If in another equation, capital N means the total turn. So so small letter and capital letter does have its meaning. They don't really choose it randomly. They really have some meaning inside. So we substitute 4 pi. 4 pi times 10 to minus 7. Pi is 1.5. And the number of turns, 220 turns per centimeter. So it is 200. So it should be 22,000 turns per meter. Because we need to use the SI unit. And the area would be pi 0.0 0.021 over 2 square, which means it is the magnetic flux across this small here, the magnetic flux for this one, for the coil C. And D is the diameter, so 0.021 divided by 2 is the radius. So this is the pi r squared, which is the area of this part. This is the area of this part. And we know that it is 1.44 times 10 to minus 5 Weber. Then we can calculate d phi d dt. d phi d dt. So actually, it is reduced to 0 at the static rate in 25 milliseconds. So it is something like minus 1.44 times 10 to minus 5 over 25 times 10 to minus 3. Because it is from 1.44 times 10 to minus 5, it reduced to 0 in 25 milliseconds. So the rate of change is minus 1.44 times 10 to minus 5 divided by 25 milliseconds. So it is something like minus 5.76 times 10 to minus 4 Weber per second. So finally, the electromotive force is something like n d phi b dt, which okay, something like this. So it should be 130 turn, 130 times 5.76 times 10 to minus 4. So it has a negative sign and we have 2 negative signs, so it is positive. So the final answer is 75 millivolt. 75 millivolt. So actually the induced electromotive force is quite small. It's quite small, 75 millivolt. So if we really need to use this to generate power, we need to changing the field very fast, or we need to increase the N, increase the number of current. So here we talk about the Lenz law. An induced current has a direction such that the magnetic field due to this induced current oppose the change in the magnetic flux that induced the current. The induced EMF has the same direction as the induced current. Here it means when just now we know that if we have a magnetic bar here and we try to change the magnetic flux through this loop, it will generate an electromotive force, and this electromotive force will also generate a magnetic field, and this induced magnetic field will be opposite to the change of the original magnetic field. So it's something like the induced magnetic field try to stop the changing of the magnetic field or the magnetic flux across this loop. Lenz law at work, as the magnetic is moving toward the loop, the current is induced in the loop. The current produces its own magnetic field, which magnetic dipole moment mu orient so as the opposite motion of the magnetic. Thus, the induced current must be counterclockwise as shown. It tells you how to determine the current, of the induced, or it tells you how to determine the direction of the induced EMF. It's something like if you have a magnetic state here, if you push closer to this loop, then the magnetic flux go across this loop is increasing. So it will try to generate another magnetic field in another direction, so that it try to stop the changing of the magnetic flux, although it may not perfectly cancel the changing, but it tries to do this action. So it tries to induce a magnetic field pointing upward, so that it will generate some magnetic field pointing to the top within the loop, so that it will cancel part of the the changing of the magnetic flux. So here we'll talk about the Lenz law. So in increasing the external field B, so B is the external field, and this external field will go through this loop, so that when you increase the external field, the magnetic flux go through this loop is increasing. So it will try to generate a EMF, something like counterclockwise. And in this case, it is counterclockwise. It will generate a B field pointing upward.
the induced current create this field, try to offset the change, trying to cancel the change, only trying, but not necessarily cancel all of them. And the finger in the current direction, the thumb is in the induced field of direction. So it tells you that the induced B field is something like this, and the current should be counterclockwise in this field. Now we try to decrease the external field B. Then, which means the magnetic flux pointing downward will be decreasing. So in this case, it is decreasing. So this loop will try to generate a magnetic field, trying to offset this changing, because it's trying to reduce. It will try to generate a B field pointing downward. In this case, when it is decreasing, the induced EMF will be clockwise. We will try to generate a B field pointing downward, although the B is pointing downward, but it is decreasing. So the induced magnetic field will be pointing downward. So this is the second situation. And the third situation is that the external B field is decreasing until it reaches 0, and then it pointing upward. So the external B field is increasing, pointing upward. Then the induced B field will still keep pointing downward, because the external B field try to increase the magnetic flux pointing upward. So it will generate a B field pointing downward. And using the right-hand rule, still the current is going clockwise in this case. So finally, the external field B is decreasing. The induced current will be going counterclockwise. So it doesn't really matter what is the direction of the external B field. It determines the derivative of the B field, or more precisely, the derivative of the magnetic flux through this loop. So at the final stage, for the external B field is decreasing, then the induced B field should be pointing upward to oppose the change and follow the right-hand rule. The current is going counterclockwise. So any questions? This is a bit complicated. EMF 是electromotive force， 就是电动式 electromotive force. You can regard it as a voltage. It is actually has the same SI unit as a voltage or a electric potential. Yeah, that's what I mentioned just now. You cannot you cannot regard it as a voltage, because the EMF is similar to a voltage, but you cannot imagine there's a voltage dropping until this point is the original point. But actually there is a current going around it. So it's something like pushing it, rotating in this loop. It's something like you have a voltage drop at every segment, but when you go back, it's the original voltage. So the voltage is not really adapt to here whenever it is whenever there are changing of magnetic field. So it is quite complicated because you need to think very carefully how does it really change. When you just look at the graph, you cannot really determine. If you just look at that graph, you cannot really determine. You can determine how B is changing, but if you don't really have B induced and without the description, you cannot really determine B induced because you need to know what is before it. At that case, B is larger. B is smaller, and then it is increasing, so that you can determine B induced is pointing upward. If B is static, then there's no induced magnetic field. That's what Faraday's law tells us. So there's another sample problem. So a conducting loop consisting of half circle of radius r. So this is a half circle and three straight sections. This is out of the magnetic field. The half circle lies in the uniform magnetic field that is direct out of the page. The field magnitude is given by B with B in Tesla and T in second. An ideal battery of with EMF E bat equals 2V is connected to the loop. The resistance of the loop is 2 ohm. The resistance of the loop is 2 ohm. What are the magnitude and direction of the E induced around the loop by field at T equals 10 seconds? Actually, okay, in the textbook, the EMF is written like this, but I cannot find this character. So throughout the slides, I use this character instead. But just take a look at. Okay, so actually, so for part A, E induced. So the magnitude of it is something like d phi b dt. Take the derivative of the derivative of the magnetic flux with respect to the time. And actually, B. Okay, so B. So B does not relate to the space. So actually, it is constant across the loop. So we can simply use BA to substitute phi B, and
A. A is a constant with respect to time. So we only need to calculate the derivative of B with respect to the time. So A is pi r squared over 2 because this is only a half circle. And dB dt is simply AT plus 2. AT plus 2. So we substitute R equals 0.2 meter. And time would be 10 seconds. 10 seconds. So A times 10 plus 2. So turn out to be 5.2 volt. 5.2 volt. And actually the direction is clockwise. Clockwise. How do we determine it? First of all, let's assume out of the page is positive. As this one because B equals this. So we consider this term is positive, which means out of the page is positive. And then finally we can calculate this is also positive. This is also positive. This is also positive. This is also positive. Which means according to the right-hand rule, this is positive. However, for the Faraday's law, there's a negative sign, so it should be in the other direction. So finally, it should be clockwise. Because this direction, according to this one, is positive. So it should be something like if outside is positive, then according to right-hand rule, it should be counterclockwise. So d phi dB is positive, which means counterclockwise. However, for Faraday's law, it should be a negative sign. So the induced electromotive force should be clockwise. And for part B, what is the current in the loop at t equals 10 seconds? T equals 10 seconds. So I would be equals to E net over R. Ohm's law. And it will be something like E bat, the battery, minus E induced over R. And the battery is 2 volts. The induced EMF is minus 5.2 over 2. So it will be minus 1.68, 1.68. And actually, this is negative. This is negative. So the current should be rotating clockwise. Induce. You can consider a equivalent circuit like this, although it is not very. It will be something like this. Something like this. This is the E induced, and there should be a resistance. This will be a 2 ohm. This is clockwise. This is counterclockwise. Or you can just exchange these two, and then you finally get something like this, And actually, this is clockwise. This is clockwise. You can only think similar to this, although it is not perfectly correct, because this E induced is separate, is distributed equally distributed within this loop. This is not a long battery. So you can write it something like this. This is negative, this is positive. And we don't exchange it. Something like this. So, any questions? So there's another sample problem. Okay, so here, figure shows a rectangle of wire immersed in a non-uniform and varying magnetic field. B is perpendicular to and direct into the page. There's a magnetic field direct into the page. The magnetic field is related to the time and the x-axis, with B in Tesla, T in second, X in meter. The loop has a width. The width is 3 meters, the height is 2 meters. What are the magnitude and direction of the induced EMF around the loop at T equals 0.1 second? So first of all, we calculate the magnetic flux. So the magnetic flux is not B times A anymore. It is B dot dA with the surface integral. The surface integral, and hopefully, it is not related to the y-axis. So it is something like we integrate it from 0 to w, and we have b. 40. BH, okay, we can write it like this, BH dx. Okay, dA is something like the height times dx, and we integrate dx from 0 to w. So we substitute w is 3, and b is 4t square x square. And h is 2, and then we have dx. So we factor out the constant with respect to x. It is 8t squared from 0 to 3 x squared dx. So it will be 8t squared 1/3 3 cube minus 0 cube. So it will be 72t squared. So we calculate phi, and then we need to calculate the magnitude of the electromotive force will be the derivative of the magnetic flux. The derivative of the magnetic flux, so it will be something like 144t. So E at t equals 0.1 second is something like 14.4 volts. 14.4 volts. And the direction we really need to determine it. So actually, pointing inside is positive, and we find that d phi b dt is positive. So for d phi dB positive, it should be something like this. And consider the minus sign. Consider the minus sign is to be something like counterclockwise. So actually, the induced EMF should be counterclockwise. Counterclockwise. Okay, any questions? If no, and that's it for today.